Welcome to the tutorial, First Modeling Steps. This video will show you the concept of modeling with CAESES and guide you through your first steps during the design process, which makes it a good starting point for getting acquainted with our software. Let's start by saving our project in the main menu, which can be found through the three horizontal lines located at the top of the gray navigation bar to your left. To save the new project, let us click on Save As and name our new project file, First Modeling Steps. For quick saving, you can also use the Quick Action button located in the top blue ribbon or simply use the shortcut, Ctrl+S. The 3D view window is located on the right. You can rotate or pan the scene by holding the right or middle mouse button. If you would like to reset the view to a certain plane, click on the cube in the lower left corner. A selection of predefined global X, Y, and Z views is also provided in the Views menu, which can be accessed by selecting the coordinate system icon with three dots inside the bottom option bar. Through the navigation bar on the very left, you can access different workspaces in CAESES. The Model workspace is used for geometry creation and modeling. The blue ribbon at the top reveals further subsections inside each workspace. In case you need help, you can open the Help section, which is located in the bottom left corner for more information. In this example, we are going to model a simple parametric duct, which will teach you basic modeling techniques and introduces the modeling concept of CAESES. Throughout the creation of the duct, you will learn how to model curves, surfaces, and solid bodies, as well as certain operations for each type. Let's start by navigating back to the Model workspace and creating a new scope via the scope icon in the top left corner. At the beginning, we need to define the center line, which will be the path for the duct sweep surface. In this case, let us rename the scope to Centerline. You can click the middle mouse button while your cursor is pointed at the scope icon in the object tree to make it a working scope. To organize your scopes, you can write numbers in front of the scope's name. Next, we want to select the curve type, planar with tangent control, as our centerline. This curve type can be found under point-based curves inside the curve section in the CAD ribbon. It allows you to change the tangent angles, speeds, and weights at start and end, as well as the start and end positions themselves. Let's rename the curve to Centerline and adjust the start and end properties as shown. To have a better view of the curve, we can reset the zoom by clicking on following icon at the bottom option bar. In CAESES, modification of your geometry is done by defining design variables, which enable quick and easy adjustments during the modeling process. Every input value that is used for creating curves or surfaces can be converted into a design variable by selecting and right-clicking on the desired value. Again, let us rename the design variable to a clear name for better transparency. Each design variable is separately stored in the object tree for easier access and control over your geometry. To show the control polygon of each curve, you can select the polygon icon inside the Display Options menu. We can also define the interval in which the design variable can be modified. To modify a design variable's boundaries, click the Edit button next to the name of the design variable to set the lower and upper bounds. When the lower and upper bounds are set, a slider will automatically appear under the design variable for a more intuitive way of changing the geometry. As the center line is now defined, we can deactivate the working scope by clicking the middle mouse button again. If you would like to have a clear sheet for your following modeling steps, you can hide objects by clicking on the scope symbol in the object tree. Next, we will create the duct's inlet cross-section. For this, we can create another scope named Profile Start and set it as working scope again. Let's create a 3D point, which can be found in the Points section at the top, and change the X and Y coordinates as follows. Note that 2D profiles for sweep surfaces are always defined in the XY plane in CAESES. After the first point is defined, we can copy the point by right-clicking on it and selecting Copy. Make sure the correct scope is selected while you paste copied objects. In this case, we need to reference the design variables in the y-coordinate of our second point. To reference objects in CAESES, click on the Editor field into which the object should be referenced and hold the Alt key while selecting the desired object. Another option is to drag and drop objects to the desired location to reference them. Another way to copy and paste objects is to use the shortcuts Ctrl+C and Ctrl+V. Let's set the x-coordinate of our third point to 0. Now we can create a curve from our 3 points. To do that, we first need to select all 3 points, which is done by holding the Control key while selecting each point. Note that the order of selecting the points will determine the direction of the curve, which can be important for certain curve operations. While the 3 points are selected, let us navigate to Point-Based Curves inside the section Curves and select the NURBS curve. Let's name our new curve to Arc 1. As the points were selected during the creation of the NURBS curve, the curve will automatically set the points as source objects in the same order as we previously selected them. The icon on the right of the Display Options menu will reveal the origin of a curve, as the direction of curves can be important for later operations, such as combining different curves with each other. Turned arrow icons next to each object editor category indicate hidden object options. Let's expand the category General of our curve and modify the weight of the middle point as follows. Now, while arc 1 is selected, let us create an image curve from the first arc by selecting the image curve inside the Curves section. Image curves are often used for trimming and translation operations, as it is shown in the next steps. After renaming the image curve to arc 2, we add a new operation by clicking on Add New Operation in the Operations section. In this case, we want to mirror the curve at the y-axis. To do that, we use the operation Scaling, which is located under Transformations. Inside the editor of the scaling operation, change the x-factor to -1. This procedure is going to be repeated until we get a closed profile. As soon as all the arcs for the starting profile are defined, select them in the correct order and create a so-called polycurve. This curve type combines the selected arcs to one single curve. It can be found under Curve-Based Curves inside the Curves section. Let's rename the polycurve to Profile and activate Auto Orientation, as this will correct the orientation of the individual arcs for a continuous resulting curve. Now, we can position our profile on the center line by adding the operation Sweep, which is located under Transformations. There, we can reference the centerline curve as the path of the profile by holding the Alt key again while we select the curve centerline. As a result, our profile is being transformed to the position of the starting point of the centerline curve, as the path parameter is set to 0 per default. This parameter defines the relative position of the profile along the centerline curve, which is determined by a so-called t-value going from 0 to 1. Let's leave the t-value at 0, as our current curve is defining the inlet cross-section of the duct, and create a parameter for it, which is the same process as the creation of design variables, and name it sweep pos. In the following step, we adjust the lower and upper bounds of each design variable in the object tree. At the end, let's deactivate the working scope profile start, as we move on to modeling the outlet profile. To model the end profile of the duct, we can simply copy the starting profile scope by using the shortcuts Ctrl+C and Ctrl+V, and adjust the values of the different design variables. As this is going to be the profile at the end position of the sweep curve, we have to set the parameter sweep pos to a t-value of 1. First, let us adjust the design variable radius to the default value of 50 and adjust the lower and upper bounds accordingly. Note that to update the design variable to the new default value, you have to click on the reset icon next to the edit button. Afterwards, we change the ellipse and weight factor to 1. This will change the outlet profile into a circle with the radius of 50 mm. Let's deactivate the working scope again. As the profiles and the sweeping path are defined, we can create the surface of the duct. Let's start by creating another scope called main duct, and make it a working scope. This time we navigate to the Surface section and select the Sweep surface, which is located under the Curve-based surfaces. After renaming the surface to Duct, we can reference the center line as our path and the two profiles as Start and End profile. Next, we want to transform the surface into a BRep by selecting the surface inside the object tree and selecting BRep at the top next to the section, Surfaces. BRep stands for Boundary Representation. These object types are used to assemble and further process surface geometry. Another important part of modeling a flow domain like our duct, which will be processed for example inside a meshing program, is the consistent naming of the different boundaries such as the duct surface. This naming of surfaces is done with colors in CAESES. Each color has an ID, which should be unique for each boundary. The ID of each color is defined by its RGB values and name. Let's create a new color for our BRep, Duct Closed, by navigating to the source object of the BRep through the Edit button next to Add Sources, and clicking on the color wheel in the Color section. Inside the pop-up window, select Create New Color. Now we can rename the color to Duct Wall, which will be the name through which we can reference this part of the imported geometry inside an external tool like a mesh generator for assigning different mesh settings or boundary conditions. To transform the duct into a closed and solid boundary representation, add a new operation in the Operations section, navigate to Closing, and select Faces from Planar Curves. Now, we reference our starting profile curve as the source object and create a new color for the operation. You can choose between predefined basic colors, adjust the RGB values manually at the bottom right corner, or write a specific HTML color code. Let's rename the inlet surface boundary to Duct Inlet. To view the color, we can simply deselect the object Duct Closed by clicking into empty space. Closing the domain at the end profile will be identical to the starting profile, except the source object will be the curve of the end profile. Again, we create a new color and call it Duct Outlet. In the final part of this tutorial, we will create an additional intake cylinder, which will be merged into our previously modeled duct. At the beginning, we are going to create a new scope and name it Intake Cylinder. As we currently don't need to see the objects from the previous scopes, we can hide the geometries by simply clicking on the scope symbols on the left inside the object tree. To create a cylinder domain, navigate to the BReps section at the top and expand the menu, More. Here, you can find basic predefined domain geometries. In our case, we are going to select the cylinder domain. Let's rename the BRep to Intake Cylinder. Now, we can reference the center line as the center vector by holding the Alt key while selecting the center line and add .get behind the referenced object. Pressing Ctrl+Space will activate auto-completion, which in this case will unfold a list of commands you can choose from. As we want to get the positional vector from a specific t position along the centerline curve, we can select the command getPos and enter a certain t value, in this case 0.3. All commands inside the auto-completion menu are sorted by their return type, which explains why this command can be found inside the section f-vector3, as the return type is a three-dimensional vector. To reveal more information about the arguments of each command, you can press Ctrl+Space while the cursor is inside the parentheses. In our case, the positional t value along the curve is defined by a type double input value, which is a floating point number. Now we can create a design variable for the t position and name it IntakePos. Next, we modify the diameter to 30 and create a parameter by selecting the value, right-clicking and selecting Create Parameter. We can change the name of the parameter to Intake Diameter and close the parameter window again. Let's adjust the length to 150 and change the axis to Y. As we want to combine the cylinder with the duct, we can select the color, duct wall, as the color of the cylinder, which will define the surface of the cylinder as the same boundary as the duct. As the intake surface of the cylinder should be defined as a separate boundary, we will create a new color and rename it to Intake Inlet. Finally, we can combine these two geometries by merging them inside a newly created scope called Final Domain. Let's click the middle mouse button again to make it a working scope and select the BRep duct closed in the scope Main Duct. Now we can create a separate BRep based on the closed duct by navigating to the BRep section, selecting BRep and naming it Final Domain. To combine the BRep we just created with the intake cylinder, we will navigate to Add New Operation, Boolean, and select Boolean Operation. Boolean operations are often used to unify or intersect different BReps with each other in CAESES. Now we are going to reference the intake cylinder BRep as the source for the Boolean operation and select the operation union inside the operation section. Normally, the union operation is set as default operation for Boolean operations, thus in this case we don't have to change it. To add a fillet between the intake cylinder and the duct domain, we can activate filleting by ticking the Active box inside the filleting section. We can increase the radius of the fillet to 10 and add another color to the fillet surface by clicking on the color wheel. In the final step, let's name the color duct fillet, collapse all the scopes and deselect everything to view the final geometry. To get a cleaner view on the final geometry, we can hide the edge lines by deselecting the green edge symbol called Display All Edges, which can be found inside the Display Options menu. Thank you for following along, your CAESES support team.